like my top. It was one of my most recent thrifts. I love it. Square neck, breathable. Today's a hot day. Yesterday was it yesterday? Yeah, yesterday. Day before yesterday was a cold day. Yesterday night was kind of chilly. I stayed. Okay, no. I went to bed for 5 hours, and I woke up at 6 this morning, and I finally got the NCBI Geo stuff to go in, so I'm proud of that. I think I put it on my list. I did put it on my list. Yeah, it's still happening. And then I went to like go relax, maybe for too long. It was 30 minutes plus. During that time that I was relaxing, my sister called me, saying she wanted us to have a family meeting, and that I'll be back in a jiffy. I got back around like 2. And then I got off my phone. It's like I should never go back to my long time home because like something bad always happens. Either I come back poopy or I leave something. Although they're both under my control, so let me not blame it on the house or the people there. I dilly-dallied a bit. I fixed a chain that was broken for a long time. I took the polish off my nails. I'm going to reshape them hopefully sometime today or tomorrow. But the most important things right now are look at lecture for class, do the assignment with everyone for 5.2 or assignment 5.2, and then after that I'm gonna have to keep working on 5.1 because I didn't do that, and tomorrow I'll do the lectures for 5.1. And then I have to keep working again to get some of the changes back from my proposal. I was saying in a video yesterday that was too long for YouTube, that last week I didn't send anything because I didn't think I'd done enough. But then when those changes were lost inside the worldwide Event's computer, it was really disheartening. Like, it felt like that was a lot, and now it's gone. Yeah. So I'm gonna have to work on that and practice the breathing. Let me do it right now because I don't think I've done it today. Maybe in the morning I did, but a lot's happened since then. So ready? It's gonna be 4, 7, 8. I'm gonna be tapping my hands or my shoulder. Hopefully I don't slow down when I'm breathing out or speed up when I'm breathing in. Let's just do a pattern. Ready? 3, 2, 1. 1. Or matter of fact, let's pull up a video. Like why exactly use the World Wide Web of the Internet? Alright. Oh, boo, boo, boo. You started way too quick. And it doesn't even time the inhaling. Itches. Okay, let's start inhaling before clicking. 3, 2, 1. It's not counting, it's just a bubble. I think I'm gonna like get straight like this. Okay, I think I feel better. So I'm gonna stop that and start working. I'm looking at I have 7 minutes. I'm gonna try to open up assignment 7, or at least like just read through it. Apartment 5.1, I meant to say. Oh no, my pictures. I've drawn my tweezers and I blended one of them, the pointy ones that can dig skin. I was so sad. You can't even try to fix it. I think I just did this with this one as well. Yeah, I did. Mother sucker. Or at least I think this one was cheap. I think I got it from Lidl. But it's actually like really good. I like how it feels. It's like smooth and like shiny. Anyways, I'm gonna put it in her. Ew. Why is my skin dark looking? I need to work on this. Ooh, look at that. Mewy. Mm-hmm. 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 I'm not gonna have a trash for them. It's not even my hat. Bitter. And I'm not bitter. Okay. What am I? I'm pretty. I need to exfoliate today. Oh my gosh. I love the color. It's like so pretty. Hibiscus. And my recycled glass jar from the old pasta sauce. I don't remember which brand this is, but it definitely is in Classico. Classico has the square ones that are cooler. I mean, Classico is not expensive, but it's more expensive than this one, so. Dude, my ice is melting like mad fast today. I have to go pour the water out. Bitches. Okay, bitches. Let's get information. Fucking bitches. carpet the entire day. So. Oh. Okay, Google. Turn off the lights. I'll leave the lights on because it makes me feel bright. Is this the trash? Put something else lower. Ooh. We are so cute. Me and my boo. Oh, Pooh. Who said you could? Charger starting to feel cold, so let me go grab a sweet treat. But let me go wear this not a helmet because that needle is a smart needle. I did the sleeve thing. I'm not completely done, but now I can do this. I love it. Yeah, I still have to sew it though. I have to finish sewing it. Ding, 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 ding. I think I'm gonna cut like this excess fabric and put it right here so that my thumb can still have some cover, at least like the base of my thumb. Time for assignment 1 is over. So I'm gonna go to Panapta Recordings where there should be
Hey everyone, so I wanted to give a brief introduction to some terminal or shell commands. Welcome back everybody to exercise that we're looking at. So this is part 2 of week 5 where we'll talk more about protein design. Welcome back, everybody, to computational virology. So this is part 2 of week 5, where we'll talk more about protein design. And this time,
Yo,
to
this
optimize
dude talks
and
so low.
and improve the scoring function for protein design applications. So previously we talked about using known data sets of binding affinities to benchmark particular scoring functions, candidate scoring functions, and figure out which might be better than others. And so we have, for instance, a set of 60 known binding affinities for this protein-protein complexes that have structures, and then we use these scoring functions to look at the structures, score them, and see whether we get a better correlation with scoring function A versus scoring function B with the experimental delta G's for binding affinity data. And we want to see which of these would reflect the known affinities better. So the idea is to use that once we selected a scoring function. In this case, scoring function A looks better. Welcome back, everybody, to computational virology. So this is part 2 of week 5, where we'll talk more about protein design. And this time we'll talk about how to optimize and make a good and improved scoring function for protein design applications. Okay, so previously we talked about using known data sets of binding affinities to benchmark particular scoring functions, candidate scoring functions, and figure out which might be better than others. And so we have, for instance, a set of 60 known binding affinities for this protein-protein complexes that.
All right, hopefully this is the
Welcome
last
back, everybody, to computational virology. So this is part 2 of week 5, where we'll talk more about protein design. And this time we'll talk about how to optimize and make a good and improved scoring function for protein design applications. Welcome back, everybody, to and this time we'll talk about how to optimize and make a good and improved scoring function for protein design applications. Okay, so previously we talked about using known data sets of binding affinities to benchmark particular scoring functions, candidate scoring functions, and figure out which might be better than others. And so we have, for instance, a set of 60 known binding affinities for this protein-protein complexes that have structures, and then we use these scoring functions to look at the structures, score them, and see whether we get a better correlation with
Watch it! I don't like the way I started. I want you to format
experimental delta G's for binding affinity data.
I'm going to pause this.
And we want to see which of these would reflect them.
Alright, there. And copy the heading here. I was about to say I need more loose paper, but that's easily solved. I have more inside my folder. This class is right.
previously we talked about using known data sets of binding affinities to benchmark particular scoring functions, candidate scoring functions, and figure out which might be better than others. And so we have, for instance, a set of 60 known binding affinities for this protein-protein complexes that have structures, and then we use these scoring functions to look at the structures, score them, and see whether we get a better correlation with scoring function A versus scoring function B with the experimental delta G's or binding affinity data. And we want to see which of these would reflect the known affinities better. So the idea is to use that once we selected a scoring function. In this case, scoring function A looks better, let's say, from what we're seeing on the right. And we would use that to predict affinities that we don't know. And because it looks the best according to our data set and benchmarking that we tested it with. All right, so scoring functions for protein design are often reflect optimized and weighted scoring functions. And so on the right here is showing like one particular function from Rosetta. This is called score 12. And so these are all these different weights that are given to the terms in Rosetta. And so at the top, it says FAATR, that means full atom, attractive van der Waals, and that has a weight of 0.8. The repulsive van der Waals weight is a little bit lower. That's 0.44. A little bit of overlap and being a little bit more lenient when two atoms are close enough together to have a sort of repulsive force between them. All right, so scoring functions for protein design are often reflect optimized and weighted scoring functions. And so on the right here is showing like one particular function from Rosetta. This is called score 12. And so these are all these different weights that are given to the terms in Rosetta. And so at the top, it says FAATR, that means full atom, attractive van der Waals, and that has a weight of 0.8. The repulsive van der Waals weight is a little bit lower. That's 0.44, and that might be to allow a little bit of overlap and being a little bit more lenient when two atoms are close enough together to have a sort of repulsive force between them. And so on through this list. There's FA-Sol is a desolvation term, and there are other terms, LR H-bond, LRBB, and et cetera. With the H-bond, those are various side chain hydrogen bonds, backbone hydrogen bonds, and they get weighted differently based on what looks best according to a set of training data that it's parameterized with. And so when we have a training set, it's important to consider various things. One thing is sufficiently sized data set. So you see on the right here, there are lots of terms in the Rosetta scoring function. So if we just have like one or two examples of protein structures or binding affinity data that we're trying to train with, and you have like 20 different terms, that probably won't be sufficient to get a good way to weight your data. And we also want to consider what's being optimized. For instance, are we trying to predict binding affinity? Or do we want to predict stability of a protein? We have a bunch of thermodynamic data from, for instance, Protherm, or loop modeling accuracy, and look at RMSTs and seeing if we're recapitulating native structures with our scoring function. Okay, so I want to talk about an example of protein design. Okay, so I want to give structures with our scoring function, seeing if we're loop modeling accuracy, and look at RMSTs and seeing if we're recapitulating native structures with our scoring function. Okay, so I want data affinity, or do we want to predict stability of a protein? We have a bunch of thermodynamic data from, for instance, Protherm, or loop modeling accuracy, and look at RMSTs and seeing if we're recapitulating native structures with our scoring function. So you see on the right here, there are lots of terms in the Rosetta scoring function. So if we just have like one or two examples of protein structures or binding affinity data that we're trying to train with, and you have like 20 different terms, that probably won't be sufficient to get a good way to weight your data. And we also want to consider what's being optimized. For instance, are we trying to predict binding affinity, or do we want to predict stability of a protein? We have a bunch of thermodynamic data from, for instance, Protherm, or loop modeling accuracy, and look at RMSTs and seeing if we're recapitulating native structures with our scoring function. Okay, so I want to talk about an example of protein design where we look at the A6 T-cell receptor. And I believe I talked about this before, but I want to dive in a little bit deeper and just talk about the protein design optimization that we did as part of that project. So we looked at the A6 T-cell receptor. We were trying to improve its affinity for the tax HLA-A2 peptide MHC. So we had a PDB of the wild type complex 1807 to look at, to compare with, and to perform modeling with in Rosetta, competing for the tax HLA-A2 peptide MHC. So we had a PDB of the wild type complex 1807 to look at, to compare with, and to perform modeling with in Rosetta. So what we did with that was we had this set of known point mutations of A6 that already had measured binding affinities. They were measured using Service Class 1 resonance in ViaCord. And we looked to see whether Rosetta, when it modeled the point mutations and scored them, would reflect the known values from ViaCord. And so that's shown over here on the right. And so we had this green set of initial data that we had measured for bits of that project, top percentage of the dynamic data from MSTs, where we looked at the A6 T cell receptor. And I believe I talked about this before, but I want to dive in a little bit deeper and just talk about the protein design optimization that we did as part of that project. So we looked at the A6 T cell receptor. We were trying to improve its affinity for the tax HLA-A2 peptide MHC. So we had a PDB of the wild type complex 1807 to look at, to compare with, and to perform modeling with in Rosetta. So what we did with that was we had this set of known point mutations of A6 that already had measured binding affinities. They were measured using Service Class 1 resonance in ViaCord.
What's tax HLA?
And to perform modeling with in Rosetta. So what we did with that is we had
Sorry.
And we looked to see whether Rosetta, when it modeled the point mutations and scored them, would reflect the known values from ViaCore. So that's shown over here on the right. And so we had this green set of initial data that we had measured. And that actually looked pretty good. There was a decent correlation between the Rosetta score, which is on the y-axis, and the measured delta G's on the x-axis. But then when we generated new point mutations based on what Rosetta thought was good, when we performed a larger scan of the interface that involved 494 point mutants of the T-cell receptor, corresponding to 26 different residues, which we mutated all possible 19 amino acids. So we looked at the top scoring ones from that large comprehensive computational scan and selected those for experimental testing. And those are the blue points on this plot when we measured them in terms of their experimental binding affinities. And we can see that some of them, in particular G28R and I54R, they seem to have a much poorer binding affinity. They're shifted off to the right versus where they should have been on this plot. G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. So the question is, can we perform improvements to this function? Because we do have a set of data. We tried the regular Rosetta scoring function. So the question is, can we do that? It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. So the question is, can we perform improvements to this function? Because we do have a set of data. We tried the regular Rosetta scoring function. It did reasonably well, but then it looked like it might not be terribly predictive in some cases based on the new data that we had. And we only had about 20 measured affinities, so we didn't have enough to train a large weighted scoring function like that one I showed you from Rosetta's score 12. It has like 20 different terms. But we did have a slightly larger set of affinities, actually much larger, so it had about 500 delta G values from enzyme inhibitor interfaces. So this was nice. So we had this larger data set to train. So this would allow us to at least explore a few more terms and maybe get a nice weighted function that would be non-redundant with the test set, which is the T-cell receptor mutations. Plus two, delta has like 20 different terms, affinities. So we didn't have enough to train make improvements to this function, finding affinity than wild type is still in the negative range on the x-axis. But G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. This is where they should have been on this plot. G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. On this plot. G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis versus where they should have been on this plot. G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. So the question is, can we perform improvements to this function? Because we do have a set of data. We tried the regular Rosetta scoring function. Okay, so I want to talk about an example of protein design where we looked at the A6 T-cell receptor. And I believe I talked about this before, but I want to dive in a little bit deeper and just talk about the protein design optimization as part of that project.
Several times.
So we looked at the A6 T-cell receptor. We were trying to improve its affinity for the TAX HLA-A2 peptide MHC. And we had a PDB of the wild type complex 1A07 to look at, to compare with, and to perform modeling with in Rosetta. So what we did with that is we had this set of known point mutations of A6 that had already had measured binding affinities. They were measured using surface class 1 resonance in ViaCore. And we looked to see whether Rosetta, when it modeled them, that it already had measured binding affinity and to perform modeling within Rosetta. So what we did with that is we had this set of known point mutations of A6 that had already had measured binding affinities. They're measured using surface class 1 resonance in Viacord. And we looked to see whether Rosetta, when it modeled the point mutations and scored them, would reflect the known values from Viacord. And so that's shown over here on the right. And so we had this green set of initial data that we had measured. And that actually looked pretty good. There was a decent correlation between the Rosetta score, which is on the y-axis, and the measured delta G's on the x-axis. But then when we generated new point mutations based on what Rosetta thought was good, when we performed a larger scan of the interface that involved 494 point mutants of the T cell receptor corresponding to 26 different residues, which we mutated to all possible 19 amino acids. So we looked at the top scoring ones from that large comprehensive computational scan and selected those for experimental testing. And those are the blue points on this plot when we measured them in terms of their experimental binding affinities. And we can see that some of them, in particular J28R and I54R, they seem to have a much poorer binding affinity. They're shifted off to the right versus where they should have been on this plot. G28M is not too bad. It's a little bit of an outlier, but at least it has a little bit better binding affinity than wild type. It's still in the negative range on the x-axis. So the question is, can we perform improvements to this function? Because we do have a set of data. We tried the regular Rosetta scoring function. It did reasonably well, but then it looked like it might not be terribly predictive in some cases based on the new data that we had. And we only had about 20 measured affinities, so we didn't have enough to train a large weighted scoring function like that one I showed you from Rosetta's score 12. It has like 20 different terms. But we did have a slightly larger set of affinities, actually much larger, so about 500 delta G values from enzyme inhibitor interfaces. So this was nice. So we had this larger data set to train. So this would allow us to at least explore a few more terms and maybe get a nice weighted function that would be non-redundant with the test set, which is the T cell receptor point mutations. So the idea is to train on the enzyme inhibitor set, which is shown here as number 1. The T cell receptor point mutations. So the idea is to train on the enzyme inhibitor set, which is shown here as number 1. And so perform linear multilinear regression on that set to derive a set of weights that would fit best here as number 1. And so perform linear. So the idea is to train on the enzyme inhibitor set, which is shown here as number 1. And so perform linear multilinear regression on that set to derive a set of weights that would best fit the experimental delta G's with the prediction for a candidate set of terms. And then this was using like a new scientific library. And we then tested that weighted function. So that would give us a weighted function, and we would test that on the T cell receptor mutations that we had already measured. And we saw which would perform the best in terms of that correlation in part 2. And so that we had various sets of different terms that we tried, combinations of between 3 and 8 terms with all these different sort of things like manual.
Okay. Oh, dude, I'm sorry. I keep forgetting that. I keep forgetting that, like, I'm recording and that's a loud sudden noise, and most likely YouTube can't, like, get rid of it. But, yeah, sorry. It's 30 and I'm still on 1.
Walls, electrostatics, hydrogen bonding, statistical potentials. We tried all these different variants and combinatorial versions of those. And we did see some functions look pretty good. And so we applied the top function based on that to score, basically to rescore those 494 possible point substitutions of the T cell receptor to see what would look best. All right, so here to score, basically to rescore those 494 possible point substitutions of the T cell receptor to see what would look best. Enzyme inhibitor set, which is shown here as number 1. And so perform linear, multilinear regression on that set to derive a set of weights that would best fit the experimental delta delta G's with the prediction for a candidate set of terms. And then, and this was using like a new scientific library. And we then tested that weighted function. So that would give us a weighted function, and we would test that on the T cell receptor mutations that we had already measured. And we saw which would perform the best in terms of that correlation in part 2. And so that we had various sets of different terms that we tried, combinations of between 3 and 8 terms with all these different sort of things like van der Waals, electrostatics, hydrogen bonding, statistical potentials. We tried all these different variants and combinatorial versions of those. And we did see some functions look pretty good. And so we applied the top function based on that to score, basically to rescore those 494 possible point substitutions of the T cell receptor to see what would look best. All right, so here's a retrained scoring function that we got. And as you can see, what were formerly false positive predictions actually look better. So this is a more simplified scoring function, basically. It just had van der Waals, desolidation, and pure potential terms. So it's pretty simplistic, but it works fairly well. So as I mentioned, we trained this on this enzyme inhibitor set. This is basically showing how it looks against this T cell receptor data set that we had. So the blue points are more in line with the rest of the points, which is great. The G28R in particular, which was a big outlier, is now much better. And we tried a couple more data points, in particular G28T and D26W. So we predicted those, and that actually turned out to be quite good because those were in line with what we expected based on the predictions. So that's this new data set here in red, is this new measurements that we made. And so this is great. So we made some new predictions. They actually correlated well with the existing data set. So this new scoring function, which we ended up calling ZAPI, seemed to be a pretty good one. All right, so what's the moral of the story? For one thing, just taking a given protein design function, some sort of scoring function from somewhere, may not necessarily work in all cases. And some might be better than others for different scenarios, for instance. And this is based on what the scoring components are, but also the training sets that are used to derive the weights. So you can try different scoring functions and programs to see what works best for your system and for your application. And you can also train your own function. So rather than just trying what's available out there in the field, you can make your own scoring function by reweighting terms, performing, for instance, multilinear regression or some other optimization. Even now, people are using things like machine learning to optimize getting models for protein folding, molecular recognition. So likewise, protein design may be another good application for machine learning. And one consideration, especially for things like deep learning, though, is you need to have a large enough data set. So you can't just have, if you just have a couple of examples, you can't necessarily get a nice robust function that would work for a broad range of new candidate substitutions or designs. And one final thing I want to point out is that iterative design and testing is often useful. So if you have the capability or a collaborator that can actually perform experiments to validate your designs, and you can see if it looks good or not. And if it doesn't look good, don't despair. You can go back and look at your function and maybe find other ways to improve it, and then make another set, maybe have that tested. If you have the capability or collaborator with the patients to do that, that's a really nice thing to be able to do, and it often leads to more robust functions and better studies. Okay, here I'd like to highlight fewer nice protein design examples, success stories, applications. So one thing I want to talk about is viral inhibitors for influenza. So this came out not too long ago in the Journal Science in 2017. So this group was led by Ian Wilson and Scripps, and they had a Fi6b3, which is a broadly neutralizing antibody that targets hemagglutinin in its stem region. And the PDB code and structure is shown in the upper right. So you can see it sort of comes in directly sort of perpendicular to the stem and engages it. And so when you look at the structure a little bit more closely, you can see that the heavy chain CDRH3, the heavy chain CDR3 loop on that antibody is particularly involved in that interaction, basically dominates it. And the question is, can one utilize that loop, given that it's such an important part of this interaction? Can you just take that loop out of the structure of the antibody and make a new viral inhibitor that's based on that loop and its structure? All right, so they show a little bit more here. On the left is a figure from that paper where they show a couple of parts of the structure of the antibody. And make a new viral inhibitor that's based on that loop. It's basically the heavy chain CDRH3, a little bit, you see it sort of comes in directly sort of perpendicular to the stem and engages it. And so when you look at the structure a little bit more closely, you'll see that the heavy chain CDRH3, the heavy chain CDR3 loop on that antibody is particularly heavy for Fi6b3, which is a broadly neutralizing antibody that targets hemagglutinin in its stem region. And the PDB code and structure is shown in the upper right. So you see it sort of comes in directly sort of perpendicular to the stem and engages it. And so when you look at the structure a little bit more closely, you'll see that the heavy chain CDRH3, the heavy chain CDR3 loop on that antibody is particularly involved in that interaction, basically dominates it. And the question is, can one utilize that loop, given that it's such an important part of this interaction? You can take that loop out of the structure of the antibody and make a new viral inhibitor that's based on that loop and its structure. All right, so they show a little bit more here. On the left is a figure from that paper. They show a couple of different antibody loops down to that stem. And then on the yellow is the one that they're interested in, that Fi6b3 antibody. And so there are some features of that loop. And on the yellow, go a little bit more here on the antibody and make a new viral inhibitor that's based on that loop and its structure. All right, so they show a little bit more here. On the left is a figure from that paper where they show a couple of different antibody loops down to that stem. And on the yellow is the one that they're interested in, that Fi6b3 antibody. And so there are some features of that loop. You can see it's almost cyclic. It's circles around if you look at it on the right. And so that they basically made a simplistic design based on that, where they just staple the loop together using these non-protein amino acids. They also sought to improve its stability and make better contacts with hemagglutinin based on key contacts that are involved by the antibody structures that target the stem. So that led to a design of cyclic peptide that is based on H3 antibody. All right, so then so that was a structure-based design that they performed. And as you can see here, they performed a lot more design to improve the improvement. And they wanted to add a crystal structure. So the initial design called P1. They solved the whole crystal structure with hemagglutinin, and they proceeded to make a whole lot more generations of designs going all the way up to P7. And this P7 ended up having nanomolar binding affinity. It ended up being broadly neutralizing for influenza, which was really cool. And if you look at the structure, it basically mimics this H3 on that antibody. So they derived it using this large peptide library of screening, providing against hemagglutinin. But yeah, so it's basically a nice combination of structure-based design with experimental screening to generate and optimize the viral inhibitor. So a related thing I want to talk about is something called peptide derived. So this is a web server where one can go and they have a complex structure. So a related thing I want to talk about is something called peptide derived. So this is a web server where one can go and they have a complex structure and generate peptides where we'll talk about experimental screening to generate and optimize the viral inhibitor. So basically a nice combination of structure-based design with experimental screening to generate and optimize the viral inhibitor. Nice combination of structure-based design with experimental screening to generate and optimize the viral inhibitor. So a related thing I want to talk about is something called peptide derived. So this is a web server where one can go if they have a protein complex structure and generate peptides, either linear or cyclic peptides that would actually serve as inhibitors for interactions. So this web server is from Aura, Schumacher's lab, which is part of the Rosetta community. So I've met her before and I'm familiar with some of her work. And so this is built on the Rosetta application. And there's actually a Rosetta application to do specifically this. So this is basically the web server format. Okay, so the workflow for peptide derived is shown here. Basically the web server format. Okay, so this is built on the Rosetta application. And there's actually a Rosetta application specifically this. So this is basically the web server format. Okay, so the workflow for peptide derived is shown here. So the input is a structure of a protein. This is Rosetta. Either linear or cyclic protein logic generated and optimized. So a related thing I want to talk about is something called peptide derived. So this is a web server where one can go if they have a protein complex structure and generate peptides, either linear or cyclic peptides that would actually serve as inhibitors for interactions. So this web server is from Aura, Schumacher's lab, which is part of the Rosetta community. So I've met her before and I'm familiar with some of her work. And so this is built on the Rosetta application. And there's actually a Rosetta application to do specifically this. This is basically the web server format. Okay, so the workflow for peptide derived is shown here. So the input is a structure of a protein interface of a complex. And what peptide derived does is has a sliding window of interface residues, so it checks to see possible interface that cuts those little stretches out and evaluates the binding energy. Interface residues, so it checks to see possible interface residues, cuts those little stretches out. Okay, so the workflow for peptide derived is shown here. So the input is a structure of a protein interface of a complex. And what peptide derived does is has a sliding window of interface residues, so it checks to see possible interface residues, cuts those little stretches out, and evaluates the predicted binding energy of a candidate peptide against the target, and basically screens computationally all these different peptides from one of the proteins to see whether it would, in principle, bind with a good affinity to the target. And in addition to that, once the good, based on the Rosetta score, peptides are identified, attempts are made to cyclize the peptides, so that would be help too. Enforce their structure, maybe make them even better binders by having them more stable and have a little bit less entropy and the ability to flop around more. And so they look for backbone or disulfide based cyclization. Okay, so the
I am
output,
going to turn on the heater because I feel cold because I've been eating ice.
And so basically it assesses the interface energies under the data structure. So it will report whether this would potentially be like 80% of the binding activity with respect to the beta protein-protein interface of the peptide that comprises a lot of that interface that might give 50 to 80% of the activity. And it will output PDB models as well, in addition to the scores and the assessment. So we can look at the structures of these cyclic peptides and these linear peptides to see whether these would be good candidates based on structural inspection and additional looking at the scores. So this is a nice server. I recommend checking it out if you're interested. It might even be used in the English project. Alright, so there's an example here that they used. So this is HTTP E1, E2 interface. And so here's a representative publication talking about showing the structure, talking about this interface. So the basic story here is that previously people have looked for inhibitor respiration from E2 interaction. And what people did here is use the peptide-derived server to do exactly that. It's computationally using the structure-based algorithm to look at the E1 E2 interface with peptide-derived. So we have the server use that as a sort of case study example. So this is reported by group that they generated a peptide-derived server. Basically, it generated a truncated version of the E2 peptide based on analysis of that interface. Made a cyclic type of that, so 13 amino acid models that E2 peptide. And shown here, example of the output is these different binding energies versus position. And in this case, they look for 13 amino acid segments of the peptide. And you can see that some have particularly good interface scores. That energy units lower down. So in that area, particularly good interface scores. That energy units lower down. So in that area, you can see that some have particularly good interface scores. In this case, they look for 13 amino acid segments. And you can see that some have particularly good interface scores. That energy units lower down. So in that area, 25 to 35 or 20 to 30 in the position of the E2 protein seems to be like a pretty good candidate. That's shown here with the arrows. What they end up selecting is that 13. All right, so there's an example here that they use. So this is HPV E1 E2 interface. And so here's a representative publication. We're talking about showing the structure and talking about this interface. So the basic story here is that previously people have looked for inhibitors for HPV E1 E2 interaction. And what people did here was use the peptide-derived server to do exactly that. So computationally using the structure-based algorithm to look at the E1 E2 interface with peptide-derived and just submit that directly to the server and use that as a sort of a case study or an example of that algorithm.
Okay, I understand.
So this is reported by that group that they generated the peptide-derived server. Basically, it generated a truncated version of the E2 peptide based on analysis of that interface. Made a cyclic form of that, so 13 amino acid long cyclic E2 peptide. And showed here, as an example of the output, is these different binding energies versus position. And in this case, they look for 13 amino acid segments of the peptide. And you can see that some have particularly good interface scores in the values of Rosetta energy units. That's lower down. So in that area, ranging from about maybe 25 to 35 or 20 to 30 in the position of the E2 protein seems to be like a pretty good candidate. That's shown here with the arrows. What they end up selecting is that 13 amino acid candidate peptide. And so this produces, as I mentioned, PDB files, score files, that sort of information. And what one could do is that previous example that I mentioned for influenza, you could feed that structure into peptide-derived and look to see if that H3 loop would likewise come up with as a good candidate for a peptide. Even though that study they performed a lot of optimization on that, it might be interesting just to see what peptide-derived thinks of that interface. Okay, so here's another fairly recent study on protein interface design. So this was from the journal Nature a few years ago. And this is from David Baker's lab. So these are the folks that developed Rosetta. So it's a large group of people that worked on this rather massive project. And so going back to week 1, and I think in subsequent weeks as well, I mentioned this story reported by Fleischmann et al., where they designed 2 proteins to bind to influenza stem with de novo, taking small protein structures, docking it, and then designing these things to bind the stem. And so this is basically a continuation of that story where the same group of people, or at least a subset of them, went ahead and made new stem binding designs. And for this, they combined computational and experimental approaches to identify the initial candidates and then improve upon their binding that they found. Okay, so for influenza, for instance, they looked at hemagglutinin as a target in this study. So they performed stepwise screening of hemagglutinin binding, and then they have this high throughput sequencing and then library-based approaches. And what's interesting here, and so sort of the workflow is shown here, where they have all these designs and sequences, and they ended up doing all this panning to end up isolating a few designs that look like good binders. And when they looked at the structures of the models of the designs, both the binders versus the non-binders, and that's shown in the lower left here on the scatter plot. And what one would hope for is that the predicted binding energy of the binders would be better than the predicted binding energy of the non-binders. And you can see here in this plot, there doesn't seem to be much of a separation at all. On the x-axis here is that binding energy. And basically the binders are mixed right in with the non-binders. And then likewise for the monomer energy, so maybe there's some sort of monomeric better stability for the binders. And maybe it's a little bit better for the binder versus the non-binders, but still it's a large distribution of non-binders, and the binders are pretty much within that distribution. They did look at mobility, so they performed other studies as well to see if key residues, based on their assessment, would potentially be able to move more. And they did see that that correlated with non-binders, so moving residues maybe seems like rather than locked-in residues in the binding mode, did seem to correlate better with the non-binders, and the locked-in residues were better for the binders. And then they looked at structurally. Of course, they solved the structure, just like they did in their previous work with the HB36 and HB80. This new design, HB16928.2.3, is shown at the bottom here. And this is a nice small design, and you can see they solve the crystal structure, and then the model basically superposes right onto their design crystal complex structure, which is a very nice result. Okay, I want to talk a little bit about one other nice area of design, and this is nanoparticles. So there's a nice review article that I'll mention here, and I'll try to share it with everybody in the files directory. So this is from David Baker's lab again. So they have this various things they talk about in the context of the broad area of protein design. And one of them is these cage-like assemblies, or nanoparticles. And so in viruses, people have already observed that viruses will often assemble into what people call virus-like particles, and the big capsids will form these icosahedral cage-like structures from the subunits. And people have recently found ways to do that with other proteins that don't initially form into any sort of particles, but if there's a protein or architecture of interest, they can assemble de novo designs based on mutating and making these things assemble better at their interfaces. And we'll talk about this a little bit more in the context of our vaccine design talk, which will be coming up soon. Another area is cyclic peptides. So this is our vaccine design. So I'm mutating and making these things assemble better at their interfaces. And we'll talk about this a little bit more in the context of our vaccine design talk, which will be coming up soon. Another area is cyclic peptides. So this is likewise talked about in that same review article. And so as I mentioned, I'll make this available to everybody. And the same team, David Baker and his rather large lab, they looked at cyclic peptides and ways that they could engineer those and make them stable and adopt certain forms and perform structural characterization, mostly with NMR, to confirm that those designs that they made sequences for and models they indeed reflected what they intended experimentally. Okay, so to summarize all this protein design area and what we just talked about, there are lots of different protein design approaches available, and different algorithms, different applications, things you can do, like remove loops, improve binding affinities, make things assemble, create new structures. And so there's lots of success stories, and as I've noted most recently just during these previous slides, even the area of virology, that people found really neat, cool applications for protein design. And sometimes success doesn't always come on the first take, and people will often have to retrain, optimize, and at the very least try to perform some sort of benchmarking up front to see what algorithm to use in the first place. And often folks that have the capabilities to do so will find it necessary or useful to perform experimental approaches to improve the binding affinities of their initial designs using things like massively parallel sequencing and library-based approaches in order to improve their chances of success by screening large sets of variants rather than just a couple that you might get from an initial sort of structure-based design. Let's fetch that structure. Right, colored by a chain. That's the same one we were looking at on Monday. So we'll select that residue we want to mutate. Oh, all right. Thanks. Nice. All right. So mutagenesis protein. So select that, mutate it to dual tryptophan. So in this case, it shows it on in this conformation, which is sort of pointing toward the GP like protein. But you see these little arrows down here, and these will, I think, hopefully iterate through different roadways. Click on them. So this is state 6 through 6. I guess there are 6 different roadways it finds. Go through those different ones. And I think all the red just denotes probably clashes. So if this seems to think that there's another atoms the same or another molecule, that's what that red stuff means. So it's probably not a good thing to see that. When you hit this button, it'll cycle through all of them and show this little thing moving around. And it reports information to some sort of string information. So yeah, it does its own little exploring. It's kind of neat. So I just wanted to give a little more because I guess some people, for whatever reason, I'm always giving 2 different versions of that sidechain confirmation in general from what I was seeing from people's submissions. So and both are, of course, are fine. I just wanted, in case people ever want to, I'll show you how to do the road selection. Okay, sounds good. Are there any questions on that? Great. We'll move on now. Okay. So yeah, today is should be fun. So last time there's this 1-point substitution design that we tried, or we did make in PyMol, a model of it, and then submitted it to this server to get a score, a C-sharp EPI. And I guess that's somewhat of a laborious process to go through all those steps. And this time we'll do something a little bit faster and more automated. So this is using the program Foldex. And instead of looking at one substitution on that position of the antibody heavy chain, we'll run through a set of substitutions on that position and another one and get all the scores and even some models for them. And so the idea is, and if people want to check out our have links, put links in here for the documentation for Foldex. If you want more background, I try to put the main stuff within this document. And if based on the last part of the last exercise, hopefully you have Foldex downloaded, uncompressed. And so if you don't already have it, it's attached to the email too, the truncated version of that 6EAY structure, a bolo-glycoprotein in that CD45 antibody. Put that in the same folder as where Foldex is sitting. And then, so Foldex recommends that you do something called repair the PDB. So some structures, they have these random weird sidechain things that these programs don't like. So Foldex has its own method to do that, what they call repair. Rosetta has its own thing called relax or fast relax that does the same sort of thing, sort of just a minimization step. And so the command for doing that is here. There's also a website that describes it in more detail. You can check that out. But so I try to put separate Windows and Mac versions of the commands because I know people have both. But this should run it, and it'll take a few minutes, and it'll cycle through all these scores and say fixing residue 1 and all that, and it'll output a repaired PDB. So the third and last step is actually running the mutagenesis now that we have a nice repaired structure of that complex. And there's a position scan function in Foldex. and this config.cfg file will have that position scan function called, and it will just, the idea here is to make small modifications to that file. I put these dummy residue names and numbers, and just check this documentation here. And it tells you how to format within an example here, and basically based on this example, you can modify that config file, and that should permit you to run it on those positions. Just execute it with that config file. I think I gave it to you as .txt, so whatever the file name is, should go after the dash f. And finally, there's an output file. And check that out. See what the predicted energies are. We'll have what looks like at least one mutant that looks better than the wild type. It'll be in the negative range. So what's that score in mutation? Well, there's also just a general question about which position between 101 and F98 looks more desirable, which has more negative scores. And that's it. Yeah, that's this whole question. See how it goes. Let me know if you have any questions.
Brian, you know in the config file, when you're like obviously listing the different mutations, can you like list different mutations for the same residue?
You can. You can list different mutations, definitely. Like specify individual substitutions.
Yeah, as long as you just put in a comma between each one, you can like do it. So say like the example there is like, you know, like it's changing residue each time. Like, can you just keep listing different ones and it would give you like all the outputs for like just that one mutation, just that one residue with different mutations?
Mm-hmm.
Yeah.
Okay. Just as a suggestion or hint, I guess, this small letter A will automatically mutate that a position to all the amino acids. So yeah, that you can use that. It's this.
Oh, I see.
So yeah, just going by this example here, you can go ahead and just for those two different positions. So you just need to really have two different things.
Oh, okay, yeah. So you don't actually have to specify like what amino acid you actually want to mutate. It's going to do all the possibilities.
Exactly. And this will run through all. 19. I think it actually scores 20, and the same amino acid, of course, is 0.
Oh, okay. All right, great.
Yep, that's hopefully should do it. Are there any more questions?
Whenever I ran the program, you said we expected to see like the delta G values as negative. Whenever I ran mine, I just got like the total energy. So I was just kind of doing the delta G myself, just looking at the wild type and then comparing it to all of the mutations. So I don't know if I input the wrong command or what.
Huh. Let's see.
Because I'm getting values in like the 200s.
Oh boy. Yeah. And that's from the position scan.
Yeah, but I'm still getting like, they're all for each mutation, I'm still getting a different energy. Like I can easily see like which ones are better and which ones aren't, but like I wasn't sure if like it was actually outputting the correct like measurement.
And you're looking through that text file for the outputs at the end.
Yeah.
Huh. That's strange. Yeah, because it shouldn't be like that. And yeah, so you already ran the repair and the mutation.
Yeah, I ran the repair, yeah.
Huh.
I did it earlier too after watching the videos, and my numbers are also in the 200s, and I also have just like a whole string of numbers in the energy file.
That's wacky.
Yeah.
Are both of you running Windows by any chance?
Yeah, I'm running Windows.
Mine is a Mac.
Ah, no, it's not the Windows then. All right. Huh.
Hold on, you said there was like an independent text file. I'm just looking at just the command prompt. It actually outputs a text file though?
Yes. I'm looking at like energies 9860 PA prepared text file.
Okay.
Oh, yeah, I'll do it.
Do I need to like input a command after to like output the text file?
This is the name of the text file that it outputs for me. Once it's done, it'll spit out a whole bunch of PDBs, I think models of all those substitutions. But I think you should be getting a file that looks like with that name.
Oh, that's weird. I didn't get any of the models either. I just got a bunch of like energies.
Is this from the repair? Or is
Okay,
this
I do have that file, so, okay.
All right.
A bunch of other files too, I guess.
Yeah, I know it outputs a lot. That you should refer to that one. But yeah, John, I'm not exactly sure what the situation is with yours.
Yeah, well, let me check my directory real quick. What is the file called again? It's the PS. Oh, okay, I got it.
Cool. All right, check that, and hopefully it's not giving you all like 200s.
Oh yeah, okay, I got it. Thank you.
Sweet. All right, cool. Yeah, so this, FoldX functionality, or the Pymol that we did last time, they're both could be applicable in the context of the project. So that's for your information. Hopefully, there are at least options.
Dr. Pierce?
Yes.
Sorry, I didn't see that things for next time, saying to download Foldex. And it's not. I tried downloading it and I tried opening it. A prompt does come up and it looks like a command screen, but then nothing happens after that.
So you clicked on the do you have Windows?
Yeah, I unpacked it or extracted it from the folder, and it's in my it's in my computer now. And then when I click it to open it, it doesn't. Something does pop on the screen, and it looks like a command screen, and it does a couple of lines and then disappears.
Right. Yeah, I noted this in an email yesterday or today. Yeah, there seems to doing that. Yeah, well, that's what happens on Windows. But if you open up the application, the command prompt application, you know how to get to the command?
I'll go check the email. Sorry.
Oh, cool. Yeah, no problem. Let me know. I can give you more information if you don't see it.
Command.
Command has two distinct meanings.
Oh my gosh.
As a noun, it means an authoritative order.
Does it do anything, or it should start listing out numbers and things like that on the screen? Does it show anything? Let's check it out. I'll permit people to share their screen. If you want to share your screen, you can. I can check it out. Yeah, it should start pretty much immediately start going through numbers, and eventually it'll return them. Yep. Right then, press return. Huh. Press up. Yeah, then go back. Instead of foldex.exe, maybe it's just foldex.
The problem is because it's not in the location you're telling it in command prompt.
Yeah, that's right.
Yeah.
Very good.
So it doesn't actually know where foldex is.
Yeah, you could check. That's a good point. Okay, thanks. Can you,
why does it go there? Is it a default or?
Yep.
so go to press down, the down arrow. Just delete the stuff on the command line, and then you'll need to change it into the right directory.
So how much is this one? This folder.
Right, exactly. So I'll walk you through it. Can you just press the backspace and just delete that stuff on that line?
Then I come
Right, type in, that's fine. Type in dir, dir.
Enter.
Yes. Cool.
Oh.
So go to desktop, CD desktop. Capital D desktop. Is that where you put foldex on your desktop?
Okay. Desktop.
No.
Where did you say foldex?
Yeah, did you put foldex on your desktop?
I think it extracts it by default, or probably it's your downloads
program.
folder.
Oh, mine got put in documents. If you have a Windows computer.
Oh, in the map folder. This folder.
In which folder?
Yeah, check to see where you put foldex, where it got downloaded to first. Personally, I put it on my desktop on Windows, but I think that, yeah, like other people said, it might be put somewhere else.
Oh, okay.
Yeah, see where it got put, and then you'll want to change it to that directory. Okay, Marina, you can share your screen. I can see what might be going on with your situation too. I saw that you're also having issues executing foldex. All right, let's see. So can you type in dir to just see what's in the directory? Oh, cool, it's in there. So press up twice. Oh, yeah. So copy and paste that command that's in the assignment file where it says like dash repair PDB. I can share in the chat too. Right, so it's that other, I put it in the chat. Yeah. Should hopefully work.
Brian, I had a question about the final value it provides you with in the text value. So what is that value? Is that just like compared to the original? Is that just compared to the standard no mutation?
Right. Yeah. Exactly. It's like delta G. And I think my recollection is, yeah, it says like in my version it says, you know, HE98F. So it even compares with itself, which should be 0.
Yeah.
On top. So yeah, that's compared to wild type, the original residue. It's all the delta G.
That's just like the binding between the whatever chains are in that, or
yeah, it's kind of, yeah. Technically, it's the total energy change within the entire structure. So it's not explicitly calculating binding affinity change.
oh, okay, yeah. So it could even be like just the change in like the secondary structure of whatever you're mutating or anything.
Right. You can get Foldex to calculate binding energies more explicitly, but this is, you know, sufficient, I think, for this exercise. But yeah, technically, I think it's just the monomeric overall energy.
Oh, okay. Yeah, that makes sense. Yeah, no, I was like wondering if it was doing the binding and was confused how it was doing that, if it was, yeah. But yeah, that makes sense.
I've done it before to calculate binding energy change in this. Yeah, there should be a documentation for Foldex, so that's really information too.
Yeah, okay.
Other stuff is involved.
Yeah. All right. Yeah, I'm all done, so I'll see you next week.
Okay, sounds good.
Thanks. Bye.
I'm finishing assignment as well. I'll see you next week.
Okay,
Thank you.
So, see you next week.
good. See you next week.
I'm also finished. Thanks for your help. See you all next week.
Well,
Hi, Brian. I seem to have an error message here. Can I share my screen?
absolutely.
Thank you. Yeah, it seems to be an error.
Huh.
Yeah.
What about that? That's a new one.
Yeah, that's a new one. Is
Okay.
it like memory exhausted or something like that? Yeah.
Okay.
Right, and it has something in there. It's just not complete yet.
Yeah, this is the, yeah, so it's doing the mutagenesis, I see.
Yes.
It's on the physician scan. So the repairing worked okay, I guess.
Yes, the repair worked. It's just in the process of doing this command.
Okay.
Right.
A little, yeah, we should write a nasty email to the Foldex developers, I guess. Just to go to bulk.
Gotcha. Cool.
Yeah.
Well, I'm not gonna do that. I'm just like, you can. Cool.
If it doesn't, if it does that, you can try one more time or something, just in case it's some sort of random thing. But if,
Yeah.
I mean, that's not your fault. So just
Cool. Thank
let
you.
me know. But interesting. Well, yeah. Sorry, I don't have any immediate suggestions for you.
Don't worry. Yeah.
Okay. Yeah. I mean, you check the syntax in your config.cfg file, and I would check, but.
It's probably just RAM exhausted or something like that.
Yeah, no type of error. It should just output as something more informative that can't find the GPU or that they can't find the residue. It was doing that for me before. Yeah, that's a weird one. Yeah. Oh, well.
Thank you.
All right, you're welcome.
Finished up here, Brian. I'll see you guys next week. Have a good weekend, guys.
All right. I know. Charlie, were you able to find Foldex and navigate to it?
Yeah, my folder is on
Okay.
the folder. But I don't know how to get it on the folder.
Right. Yeah. So you have to run a series of or a cd command to change into that directory. I'll
I think the folder is sticky, but no that.
I see. I'll send you the commands for that, or through the chat. I can use that.
Oh,
If I had a Windows machine on this, I would just share screen and show it, but I'm using my Mac. I have another Windows machine here. Okay, I'll let you know in a minute or two.
I'm a little confused because the installation of my normal software.
Yeah, don't worry about it. Yeah, this is a different sort of beast this time. So, but I'll send you the information.
send it back quick.
Okay, great. Yes, we.
Alright, finished as well.
Right. Sounds good. Next week. Yes. Cool. Mhm. Okay. Yes. Okay. That looks fine. Oh, yeah. Okay.
Um, could you go back?
Can you show me your command prompt again? Okay. How about just CD desktop? Cool. Now type dir. All right. Yeah. So there should be that CDMG 688G folder is in there, I think. So CDMG. Well, first CD space. Cool. All right. And then type dir again. See if there the full X is in there. All right. Cool. So you should be able to CD into one of those full X directories, whichever one. Yeah, see if I don't remember if it's a little bit execute button. That doesn't seem to have it. Type CD dot dot. Just, 2 periods. That'll go into the parent directory. You'll have to go. So you go type in CD dot dot. Right, this space. CD space dot dot. Right, get rid of that. Put a space between CD dot dot. That's right. All right, cool. Now you're back in that CDMG 688 directory. You can CD into that other fold X directory. That looks like it must be what had all those files in it. Just do CD space and capital F. Then type a tab. The tab key. Maybe it'll auto-complete. Huh. It seemed like there was another foldex directory there, so maybe you should be moving CD into that.
Oh, hello? Okay, can you share your, this is how I did. I think it's slightly easier. Do you mind sharing your whole screen? Just so I can see command and the file window together? I have,
Oh, press return.
oh, it worked?
Yeah, that's the part worse. Alright, type in dir again. Cool. Then CD foldex.
Oh, nice.
Yeah, that looks like another directory. I think everything is in there, from what I remember.
No, 6EA wasn't in there. From what I saw.
Alright, type in dir. Let's see what's in that directory. I think that has everything. Yeah, type in dir.
Oh, it is in there.
Okay, you're good. I think you should be able to execute that repair PDB command now from the assignment. Yeah, give that a shot. I think that directory looks like it has everything you need. Okay. No, you don't need to have the .exe. I don't think. Yeah, it looks like you might not have the Windows version on there. Go. Okay. Instead of foldex.exe, could you change that, press up, and then change that to foldex just without the .exe? You can press the up arrow. See what's in that folder, the Win32. Wow. Okay.
I downloaded two folders for the folder. What about this one? No.
Right, shall we, can you try to copy and paste what I have into the command prompt and see if that works? Maybe Win32.0. Okay. Oh, nice. All right, try that. Uh-oh. Oh, you changed out of the directory. Okay. Should. Can you CD back into that FoldX directory? 134. Yeah, that one, just you can copy and paste that, the one that says FoldX-2020. It's okay, type in CD dot dot. Yes. And then CD FoldX dash, then tab. Oh. No tab in it, yeah. So, right, then enter. Okay. And, okay, so type in dir, yeah. Okay, so CD FoldX one more time. Okay, so try the bottom, copy and paste the bottom thing, what I sent you in the chat. See if that works. Ah, yes. Thought that would work. Okay. Let's see. So do CD FoldX 132. Oh, I see. 0. Okay, try that. Cool. Awesome. All right, so that one. And you have the PDB file in that directory. So if you use that same command, you should be able to have the rest of the command line, that dot command, will repair PDB after it, and that should run it hopefully. So press up twice. Yeah, press the up arrow a couple of times. That'll get you to the previous command, or it should. Maybe the up arrow gets to the previous command. Anyway, copy and paste that, the foldx.exe again, but don't press enter.
The full Windows.
Okay, right. Okay, then, okay, so if you press the up arrow, that doesn't show that same command.
No.
So paste that again, but don't press enter.
doesn't try to separate just the format. No.
Okay, I'll make a single sheet. Alright, so yeah, if you can get it all on the same line, if you know what I mean, with a foldex.exe followed by all that other stuff, then that should run it for you. Cool. Good, that's ready now.
Oh.
Yep, it'll just take a few minutes to run, and then after you're done with that, then you can run that other part, the foldex.exe, then the config.cfg. Once you alter that.
It's really very well.
Oh, you're welcome. I'm glad that worked.
Okay.
Brian, I have a question. So for each amino acid, do we need to make a separate text file or just position them all in the same file? The substitution?
Yeah, and the config.cfg, you don't need to specify them all.
Just one at a time?
You actually, it will automatically scan all substitutions at once. Let me show you. There's a command. I mentioned it at the beginning of the lab. Cool. So if you see this example from their Foldex website, where it says LC43 and then small letter A.
Yeah.
If you put the small letter A instead of an amino acid.
Yeah, I put small A.
Okay, cool. That'll do all the substitutions at that position.
Oh, okay.
All 19 amino acids. So that's all you need. You don't need to say Alan and all the other ones separately.
So the zeros were just placeholders, right? So I just put them. Okay.
Change those into the amino acid number, the residue number, amino acid data of interest, which I think is in the assignment file.
Okay, thank you.
Oh, I have a question about the positions also. When you say F98, like what does the F refer to?
That's the wild type residue, phenylalanine.
Okay. Alright, so when we're putting that position into the config CFG file, it would be HC98A.
I think it's actually the other way around. I think it's FH98 and then small letter A. So the amino acid name should go, or amino acid letter should go first.
Okay.
Right, yeah, FH98A should work.
Oh, we're doing this by chain. I thought that H would refer to. Wait. Oh, that is H. Okay, never mind. I'm not having chain, but H chain. Got it. Where was one? Does this application, when it's using the config file, does it test the two locations in tandem or individually?
Individually. It'll scan one position and then it'll go to the other one and scan the other one. With the other position will be one-click.
Okay.
There might be some way to get it to do both at the same time, but yeah, this just does it individually.
Well, my phone has still running.
The repair,
Yeah, the repair.
okay, it should be done soon. They usually, it might take like 10 minutes or so. Yeah, protein design takes a while sometimes. But yeah, I'm guessing it'll finish pretty soon for you. We'll involve a little bit utilizing those. And I want to at least have an opportunity to describe at least the basics, rudimentary terminal commands that one might use. Okay, so unfortunately, Linux and Mac have slightly different conventions and command names than the Windows versions, but they have the same general ideas, and they just have slightly different syntaxes and names. So for instance, if you're in a directory, so if you get your terminal application open on Linux or Mac, same sort of thing, a command window open on Windows. When you want to see what's in your directory that you're in that particular terminal session, you type ls for Linux. But in Windows, you type dir in the directory, and that will list the files in the current directory. And then other commands are noted below that. cd, change directory, clear the screen, make a new directory. And some of them are indeed the same between Windows, Linux, and Mac, but some are different as well. So this is just a short summary of a couple of commands, and I want to direct you to a larger set of commands shown at the bottom link here, especially for the Windows users, because I know that if you're using Windows, might not often use the terminal to get the use the user interface. But this is a useful thing to have, especially some computational programs that are using the terminal to open the application, make commands. So this is a nice thing to be able to do. So I want to get that to be able to open this at least some groundwork in case you're interested in exploring further, or at least learning a little more about the basics. Okay, so as an example, I wanted to give sort of a directory navigation commands that one might want to use. So on the right here is showing at least somewhat of a graphical depiction of directory organization that one might navigate through. And so if you're starting in a directory initially, and there's a subdirectory for that called home, that has files 1.pdb and stats.txt. And then within that home directory, there's another directory called stuff. And that has this other PDB file, 2.27, and then a file.
I have about 5 more minutes.
File.txt.
Yeah, if you have any more questions or
I'm showing a little bit more of the things here to navigate through those directories. So initially, before I get going, let's see home. So that brings you from your initial directory to the home directory. And inside that home directory, and then if you type dir Windows or ls for Mac or Linux, you see the names of those files.
The question that asks which one's more designable, would that have to be based on which position has more low numbers than the other?
Exactly. That's right.
Alright.
The question is a little vague, I know. Yeah, that's what I meant.
Yeah. I was asking because I didn't see that term in the Panacto.
Yeah, I was sort of going outside the box with that term in question. I just that's what I meant though. Just more possible ways to improve that position.
And I did look into it, but maybe you might be able to give me a clearer explanation. So TAX is a peptide, and then the HLA-A2. Could you please explain what that is a bit more? I see that it's like a serotype and an antigen, but what is it? It was hard to find out exactly what it was because everyone was using it as something that you should already know what it is.
Right. So it's an allele of a molecule called the MHC. So that everybody has 2 copies of the HLA-A, one in each chromosome, with this MHC molecule. So it's a human protein, but it varies a lot among different people. So some people have HLA-A2, some people, I don't have HLA-A2. In my case, I have HLA-A3 and HLA-A27. But these are just different versions of this MHC molecule. And the MHC sits on the surface of our cells and will present peptides from within the cell.
Okay.
That's what the TAX peptide is. It's a viral peptide that is presented by that particular MHC molecule.
And this is, I took virology, and the MHC term is, what is the word? It rings a bell. And this is like, well, it's a molecule that sometimes when the viruses infect a cell, they try to get the cell to stop making these because it's basically a telltale. It's the cell trying to tell the rest of the body that, look, this virus is in me and it's making these proteins. Come kill me. Okay.
Yes, exactly. Yeah, some viruses, like you said, they'll downregulate MHC.
Okay. All right. I'm just waiting for the program now. Thank you. Oh, but I can stay on and whatnot. Yeah. Never mind.
Okay. Well, I think it's going well with the full X. It's good.
That has to be with our type message. Should I have to this command both types?
So that's the file, right? That's the config.pfg file should contain that. And then, in the assignment specification, so that you'll want to put that. Yeah, put that in the command window.
Oh.
So that'll execute foldex again, but it'll tell foldex to read in that config.cfg
Oh,
file that you just entered.
but I need to modify the amino acid. Oh,
Yeah, that what you sent looks fine.
okay.
So if that's what's in your config.cfg file, then that should be fine. Foldex will read that in and process those.
Okay, very quick question. I'm not sure if I'm adding the right positions. So I added just as amino acids, and then I realized maybe I need to add chains.
Mm-hmm. Chains, yes.
And I added C. Was it something correct, or because what's happened? I'm getting the result from foldex that there is no specified residues found. So I'm thinking
Yeah. So let's see. So yeah, so it'll be FH. So just as an example, the first one would be FH98A, so it means phenylalanine.
H on H. Right. Okay, I see no mistake. I put C.
Yeah, so there's no C chain. I guess and then likewise for that other residue.
Okay, then I will probably rather than.
Charlie, did that command start running? Did that work?
Yep, everything else ran. My son is here, so he's helping me. He's like, oh, thank God, with all the commands.
Oh,
Well,
my file is not found.
Oh, you have to put it in the same folder, Shelley.
Yeah, I put it under the folder I
Is it config.cfg.text maybe? If that, maybe just change the name to the, what's the name of the config.cfg file you had?
prefer config. Yeah.
You should be able to find that then.
I think it's probably text, because mine turned out or became text also after I modified it.
Yeah, Windows might have done that. If you type in dir, it'll say what the name of the file is.
And then also you can use tab to finish it once you start typing config.
Yes, it's a good tip.
Oh my God.
Oh, it works.
Is it running, Charlie?
Output text.
I'll put the file here.
Yeah.
Here is the
Okay.
yeah.
So go back to your command window then. That's fine.
Yeah. Yeah.
All right.
That means I clear.
No, that's fine. No, that's good. So, copy and paste that command again.
The command.
Yeah, then do .txt. I think as a .txt might be needed at the end of the config file. Type in dir, dir. Yeah. So you see the config.cfg. It has a .txt at the end of it. So you'll need to. That's why I can't find it. It's looking. It doesn't know to look for the .txt. Yeah, that should work.
Oh no, stop. Yeah, cancel. Press back, stop. Press the up button, the up arrow. One more time. And then .txt.
Oh. Oh, I got one color.
Yep. That's awesome. All right. Yeah, thanks for that help.
Yeah.
Yeah, this will take a few minutes too, but that should output the energies, and you should be all set.
Oh, thank you. Yeah, I have responded to the job later.
Cool.
See you have. Yeah. Bye, Brian. Thank
All right.
you.
Thank you.
Bye, everybody.
Yeah.
Bye. I should end. Oh, everyone left. Minus 9. Minus 49. Minus 4. Minus 4. Alright, that took me 1 hour and 34 minutes. Where is it? Yo. Too many effing papers. Flying effing around. Do you see that? Like, what the crap? Where are they coming from? It's about to die. This is the second one. It knows I'm coming for it. Now it's climbing. I don't want any touching to happen. Bitch! Ah! Now I hate you even more. Like, no, itch. You can't fit, motherfucker. You can't fit. That's not the crap you came through. Bitch! Now you want to go die next to my plant? Who do you effing think that you are? I see you scared. You scared, you scared. Motherfucking bitch. Look at this. You shouldn't have come in here in the first place. I'm gonna be nice and I'm gonna take you outside. Don't you go touching me. Ah, you wanna come in my house again? After all of that? Yeah. Yeah, no, I called Root Insurance and I ordered for them to come jumpstart my car because that's possible. And like these motherfuckers said they were going to send me an email with the number because I don't have a phone. And there's no email about someone coming. I mean, like, yeah, so it's quarantine, but you don't know where I need to go, motherfuckers.
So what, they never sent anyone?
No, they never sent an email, and like I told them that the person's gonna need to knock on my back door, and nothing.
Have you called again?
It took so long to even get to a customer service associate. Like, I stayed on the phone for an hour, babe. That's why when you called me, I couldn't pick up. I mean, not like a 6.
Well, I guess the only thing you can do is try again tomorrow. If nobody answers, chew their ear off. Or if, when somebody answers, chew their ear off about how today you were waiting forever and nobody ended up showing up. Obviously don't yell at the person who answers the phone because they're not the one that did the dirty. But just make it known to them, like, hey, like, I got kind of screwed over yesterday, and it's like, what am I paying for? You guys said you were gonna send someone out here, and then no one came out.
Yeah. And it's so annoying. Like, they better not count this because apparently